So far we looked at polynomials which were smooth and continuous functions. In other words, smooth, we said they had no sharp corners, and continuous, they had no holes and gaps in their graphs. Now we look at rational functions, and these have the form p of x, let's say, over q of x, which is essentially just a polynomial divided by another polynomial. For example, I can have f of x equals 2x plus 1 over x minus 1. That's just a binomial over another binomial. And if we look at this example, we know from before that this function has domain issues, and namely, there's things that go wrong here, and we know that x cannot be 1, because if it is, then I have division by 0. Now our goal is to kind of get an idea of what the rest of these type of functions look like, and we're going to analyze them by looking at a simple case first. So in example 1, by looking at this function and analyzing it near the origin, to begin with, we know the function is not defined when x is equal to 0, because I'll end up with 1 divided by 0, which will be undefined. Now let's see, when we say undefined, what happens in the nearby region close to 0. And since I can get to 0 from two sides, we're going to go look at it from both sides. So 0 is in the middle, we know. What happens to the graph when I walk towards 0 from the left, and also what happens when I walk towards 0 from the right? So those are the two cases we're going to look at for this function 1 over x. So let's say I'm going towards 0 from the left. I'm going to put some negative values getting closer and closer to 0. If I put negative 0.1, let's say, into my function, remember this is my original function, I'm going to have 1 divided by negative 0.1. When I plug that in into my calculator, I'm going to get a negative 10. If I put negative 0.01, I'm going to have divided by that number, and I'm going to end up with negative 100. And if I go even closer, really close to 0 from the left, and put that tiny number in the denominator for the function where the x is, I'm going to end up with negative 100,000. So now I'm going to do the same thing from the right, going positive numbers and putting them in. And if I do that, you'll see I end up getting a big positive number on the right side. And I end up with 100,000. And so we imagine if we get closer and closer to 0, this is going to go to, let's say, minus big number, and this is going to go to a positive big number. So mathematically, we say for the left part, I'll say, hey, I'm going to 0 from the left side, and my f of x is blowing up, or down in this case, to going to like a negative infinity. And mathematically for this side, we're going to say, as I'm getting close to 0 from the right, my y values, my f of x, is blowing up and going to positive infinity, because they keep getting bigger and bigger on the right side, and they keep getting smaller and smaller on the left side. Remember, because it's a negative big, in other words, really tiny number. So large in absolute value, but a negative in front of it. And basically, if I were to like go back to what's happening from the left and the right and put a y-axis there, it looks like when I go from the left, my function gets really tiny, negative infinity it goes to, and when I go to it from the right, my function blows up and gets really big. So I'm walking towards from the left and the right, and my y values are blowing up all the way to infinity or down all the way to negative infinity. That's by just doing a table analysis. So when a function outputs get really large or really small, it's said that f has a vertical asymptote there, and we'll abbreviate that VA from now on. So here in this problem, we can see that the vertical asymptote would have to be x equals 0, because when I approach 0, it blows up and blows down to infinity and negative infinity from the two sides. So we're basically saying vertical asymptotes. What do they mean? F of x has a vertical asymptote at the value a, for whatever that x value is, if the function goes to plus or minus infinity whenever I walk towards that x value, either from the right or the left, it doesn't matter. And vertical asymptotes, remember, the graph will never cross them. The graph will approach them but never cross them. So what are the things that could happen? Basically, I could have, as I'm approaching a from the left, it could go all the way up to infinity, Or maybe I'm approaching A from the right and it's going all the way to infinity for the graph. Or maybe I'm approaching A from the left and it's going all the way down to negative infinity. Or maybe I'm approaching A from the right and it's going to negative infinity. So anything like that happens, that means A is a vertical asymptote. So now that we have vertical asymptotes analyzed, let's go look at example 2, and it asks us to analyze the end behavior of the same function we were looking at before. So from polynomials, we know that the end behavior has to do with what happens when you walk over to infinity or you walk over to negative infinity. So when x gets really large going to the right or small going to the left. So let's, just like before, look at a table of values by making the x values big and small. So now I'm basically interested in, hey, what happens to my graph when I walk all the way to the right, or to the left in this case with the red little person, and then all the way to the right with the green person. So if I'm walking all the way to the left, remember I'm interested in this function 1 over x, so I'm putting in 1 over negative 100 in my x's, and that's going to give me negative 0.01. If I put negative 100,000 in my function, that's going to give me something even smaller. And basically, similar things happen. You'll see if I go put a negative, let's say, big number, like negative 1,000,000, this is going to go close to 0. It's basically going to become a negative tiny number. And then if I go from the other side and I put some big x value in there, that's going to become, again, close to 0. But it's going to be a positive tiny number, as you see from negative 0.01, negative 0.001, and so forth. And same thing, negative numbers that you're getting on this side. So basically, if I were to imagine a y-axis there, when I'm going from the left, they're all negative numbers getting close to 0 as I walk over to negative infinity. And as I'm walking over to the right, they're all positive numbers but getting smaller and smaller and going closer to 0. So basically, we say when the function outputs approach a finite number when x goes to negative infinity or x goes to positive infinity, that function has a horizontal asymptote. We call it HA, we abbreviate it. So in this problem, there's a horizontal asymptote at x equals 0, at y equals 0. Because as I walk over, the y values approach 0. So for the formal definition, we say f of x has an horizontal asymptote at y equals b, whatever that number is, doesn't have to be necessarily 0. If as x goes to positive or negative infinity, then f of x, the y values, approach that number b. And we got to keep in mind horizontal asymptotes may be crossed by your graph, whereas vertical asymptotes never get crossed. Now, based on what we've talked about, we're going to go look at the TI calculator to see if our analysis makes sense for this graph. Remember, we concluded that there's a VA at x equals 0, and we concluded that there's a horizontal asymptote at y equals 0. In other words, f of x, the y values are going to positive or negative infinity near x equals 0, and as we're walking to the left or to the right, meaning going to positive or negative infinity, the y values are approaching 0. Let's go look at it on our TI. All right, we're going to go put 1 divided by x, that was our function, and we're going to push graph. And notice, even though the TI looks like it's cutting off the top part and the bottom part, based on our analysis, we know that if I'm walking from the right, I'm going to... So as I'm walking over from the right of 0, where I'm standing, they go to infinity, and from the left, they go to negative infinity. And also the TI is a little misleading. It looks like it touches the x-axis. It doesn't really touch it. If I'm walking to infinity, it goes to 0 from positive values of y. And if I'm walking off to negative infinity, it goes to 0 from negative y values. So it looks like our TI confirms the table analysis we did. So we looked at one example in detail with tables and with graphs. Now we're just going to basically conclude, how do you get vertical and horizontal asymptotes from just by looking at the equation of the graph given quickly? Essentially, for rational functions, the VA just come from the denominator set to 0. That'll pop out your vertical asymptotes. It's basically where all the domain issues occur. And the horizontal asymptotes come from degree analysis. You basically look at the degrees of the numerator and denominator and see what happens. And we'll look at examples of both. Without even really looking at graphs, we'll be able to get vertical and horizontal asymptotes quickly. So for the example we just looked at, 1 over x, from the denominator becoming 0, I quickly have my vertical asymptote. Just set the denominator equal to 0. And for the HA horizontal asymptote, basically you're thinking at, okay, the degree of the numerator, it has no x's, so the degree in the numerator is 0, and in the denominator there is an x to the 1, so the degree in the denominator is x to the 1, just 1, and the denominator wins over the numerator because the numerator has a smaller degree than the denominator. So in other words, when x's get really, really huge in this case, you have 1 divided by huge, which goes to 0. So degree on top is less than the degree in the bottom. So for example 4, let's quickly, it just says get the vertical and horizontal asymptotes. The VA is going to be really quick. The denominator is 0. All right, x equals 3 equals 0. That means x must be equal to 3 is my vertical asymptote. Done there with the vertical asymptote. For the horizontal asymptote, the degree on top is 1, and the degree in the bottom is also 1. Since the degrees are the same, the guy that really, really takes over when x gets large or really small is the 2, because you essentially are looking at it as, all right, I just have 2 to the x over x. These guys go away, and I end up with 2. Formally, how do you show that? You divide all by the highest power of x in the denominator. In other words, who's winning over when x gets really large or really small? So formally you're saying, okay, 2x divided by x divided by x, the minus 3 divided by x, everybody got divided by x, which means now I have a 2 over 1 minus 3 over x. And as x gets really, really large or small, so on the side I'm just going to say if x goes really big or small, because that's what happens for horizontal asymptotes, this guy is pretty much a loser that dies out. 3 divided by something large or negative infinity goes to 0, so you end up with just 2. In other words, just the leading coefficient up here that we had seen is all that matters. So for vertical asymptote, it was easy. It came out, popped out from the denominator. For the horizontal asymptote, it wasn't so hard. If we were to just look at it visually, degree on top and bottom are always the same, so it's just the leading coefficient that matters. It's essentially 2 over that leading other coefficient downstairs, 2 over 1, which is the horizontal asymptote. So just for part A, basically, I have concluded that at x equals 3, there's a vertical asymptote, and at y equals 2, there's a horizontal asymptote. Those are the 2 pieces of info I had to find for that one. We'll look at the next examples, part B and C, in the next video.